and then we'll mic you up this way.
Okay. So now that class has started, I just put up the warm-up on the board, and there will be a Polev question for this, but just give us a minute on that. But yeah, you guys can think about this for like 4 minutes. Hello, is the mic working? Okay, great. We just posted the Polev, and it is on Ed, with the lecture slides also posted on that Ed. So I'll give you guys like maybe one more minute to fill that in. And one, I guess, little hint for this is just think about answering this in terms of n. So yeah, I'll give you guys a minute now. Okay, it seems a little quiet, so I feel like people have gotten their answers. Does anyone want to be a brave volunteer and tell me what they thought that the size of memo should be? Yeah, so he said n plus 1, and essentially we know that we want to return memo of n, but then we also know that we want some spot holder for the value when n equals 0, since that is a possibility. And so the size of the entire array is going to be n plus 1. Does anyone have any questions on that? Okay, great. So just some announcements. Exercise 5 was due yesterday, and exercise 6 is out. If you, for some reason, need one more attendance to make the attendance exercise drop policy thing, we are making a section 9 attendance as a makeup attendance. And then also, please remember that the final exam is this Friday, so that is in 2 days. If you cannot make it, if something happened, please reach out to us as soon as possible so that you can get a makeup. And additionally, all midterm grades are released and the regrades are open. So please take a look at that as well. Any administration questions?
Will there be resubmissions to the final?
Yes. The same sort of process as the midterm. Anything else? Oh, yeah, and the solutions to the midterm are also posted, the solutions. Yeah. Okay. If no other questions, then we will get started with the first problem. So this is the box problem. And essentially, in this problem, you are given n number of boxes. And so this is just a list that is your input. And each input has a length attribute, a width attribute, and a height attribute. And we want, given this list, we want to find the height of the tallest possible stack. And so you can only stack some box on top of another box if the width and the length of the box on top is strictly smaller. So if the box on top has the same length as the box below, they both have the length 2, you cannot stack that. And then here we've given sort of an example input that you would get. And so these 6 boxes, is there a laser pointer? Hold on. Okay, so these 6 boxes are an example input to what you'll get, and this is sort of the example input array. And then this here is the actual answer for this particular small input. And so we're going to use this to sort of inform how make sure that whatever we are doing and however we are solving the problem is solving it adequately.
Okay, I'm sorry, I'm going to change the lighting. Is that hard to see in the back? Okay, that's not you, that's the room. Okay, hang on, we're going to do... Okay.
Oh,
jeez. I don't even know what that's supposed to be.
Was that note-taking?
Was that note-taking?
There's no way you can take notes in this. Oh.
Better? Okay. Sorry for the interruption.
Okay, yeah. So does anyone have any questions on the problem itself? Okay, cool. So the first step to solving any problem like this is we want to identify the cases. So the way that I like to think about dynamic programming problems is sort of like a recursion problem. So in every recursion problem, you have like a base case, and then you have the recursive case. So the base case is always going to be the easiest problem that you can solve. And in this case, the easiest problem that we can solve is if the set of boxes that we can use to stack includes just one box, then the max height is just going to be the height of that one box. That is the easiest problem that we can solve. Getting rid of this laser pointer. Okay. So the base case is when the set of boxes that can be used to stack only has one box. And in that case, there is only one, the max height with that set is just the height of that one box that is in that set. The recursive case is if there are any more boxes in that set of boxes that can be used to stack. So the other way I want you guys to think about recursive cases is we have this set of boxes that we already know the answer to. We already know what the max height can be with this set of boxes. Now, if we're adding one more box to that, how does the answer that we know for this set change? And so the way that it changes is we take the max height without this box, and then we try to take this box and stack it on top of any other box inside this set. And if that height, if that stack is taller than the current max height, then that overrides it, and that is the new max height. So essentially, in the recursive case, we are finding the largest value between the height of the current box plus the max height possible with any box from the set, or the current possible max height without using the current box. Does that make sense? Any questions so far? Okay. And then this next part is a little scary because it looks a little mathy, but and I say that it's optional, but I think that it helps a lot, and it has helped me a lot. And so this is essentially the exact same thing as identifying the cases. It's just writing it in a more math-type way, which helps when you are actually writing the code for it later. And so as you can see, this case right here, this is just the base case. So if the set of boxes that we can use only has one box, the max height, which is the value stored in memo, the max height is just going to be the height of that particular box. And then this is the recursive case, so in any other situation, it's going to be the max between this and this. Any questions? Yeah.
So for the max, wouldn't like h subscript I plus memo j always be greater than memo j?
So for the most part, I think, but it also depends on whether the current box, so box I, can be stacked on anything else. Yeah. The other thing is, so memo j can be anything in the box. So like, let's say that you have this box here, which has a height of 3, and this box here has a height of 2, and then the current box has a height of 1. And then let's say that this box can only be stacked on top of this box. But then this is the max height here, right? So then this is not going to override this one. Any other questions? Okay. And so now the next step is, so we have defined sort of what goes into memo. Now we want to figure out what the dimensions of the data structure are that can store memo. And so since memo only has one indexer, it means it's only going to be a one-dimensional array. And now we just need to figure out how many dimensions that is, or how large that array is going to be. And in order to do that, we think about what this index represents. So this index represents each box, or like the set of adding one more box. Let's see, if I go on the last slide, I define this set to be all the boxes in input from index 0 to index I. And so when I equals 0, it's going to be the set of boxes from index 0 to index 0. So just the box at index 0. Does that make sense? Okay, so can anyone tell me, in terms of input, or the size of input, how many indices will memo need? Okay, that's fine. So since each index of memo is going to be sort of one more box that we are adding into the set, and since the number of boxes is dependent on our input, the number of indices that memo will need is going to be the length of input. And so memo is going to look something like this. And then let's say at index 2, what this means is the value here is going to be the max height possible using all 3 of these boxes. Any questions so far? Okay. The other thing that I am going to say is before making this, I have sorted input based on the length. And so that way, we can ensure that the next box that we add will always be on top of the previous boxes. It can never be underneath. Okay. So the next question is, now that we have figured out how big memo is going to be, one of the values stored inside memo is going to hold the final answer that we need. So whatever this function is going to return. And we need to figure out at what index of memo that final answer exists. And to do that, we think back to the actual problem. So the actual problem says, given this entire input of all of these boxes in input, what is the tallest stack that we can make? And so at any index I, so like this index I, we are storing the highest possible stack using this set. So at what index do we store the highest possible stack using all the boxes? Yeah, exactly. So it's going to be the last item in the array, and since the size of the array is input.length, that index is going to be input.length minus 1. Any questions on that? Okay. And so now that we know that this is where our final answer is going to be, we want to figure out, so we know this is our final answer, and we know this base case is when S of I has 1 box. So this is our base case. So knowing these 2 things, we need to figure out in what order we are filling the array, whether we are going to the left or we're going to the right. Okay, so what do you guys think? Raise your hand if you think it's left. Wait, I need to know my lefts and rights. Okay, raise your hand if you think it's left. Raise your hand if you think it's right. Yeah, perfect. So since this is the base case, and over here is the final case that we need, the final answer, we want to start with the base case and then move in that direction. Oh, okay. So now at this point, I like to sort of try and solve this small problem with all of the information that we have so far. And so we'll start at index 0, and index 0 we already know is the base case. And so that is just going to be the height of the box. And so the height of this box is 3. Next, we have this case. So now in I equals 1. And so we go into the recursive case. And so we want to find whether this can stack on anything previously. And since this width is 6 and this one is 5, it cannot stack on the previous one. And so we just want to check the height of this one versus this one. And so the max height is going to be 3 here still. Okay. And now the next case, I is now 2. Again, this is the recursive case. So first we want to find out what the actual max height is without this box. And so that's 3. And now we can see if we can beat that. So can we stack this box on top of this box? Thumbs up or thumbs down? Yeah, we can, since both 2 is less than 3 and 4 is less than 6. And if we stack that, 2 plus 1 equals 3. So currently, max height is still 3. Let's see if we can beat that. So now we check it with the other box as well. Can the blue box fit or stack on top of the red box? Thumbs up or thumbs down? Yeah, because 2 is less than 4 and 4 is less than 5. And so when you stack this one, 1 plus 3 is 4. And so 4 is greater than 3. And so now the max height here at this index is going to be 4. Because the max height that you can make stacking this set of boxes is 4. Any questions so far? Okay, great. That means that you guys are confident enough to fill in the rest. So I will give you guys a couple minutes to talk amongst the people around you and try to fill in the last 3 boxes. Okay, I think because of time, I'm going to sort of stop it here. On your fingers, what do you think the value is at index 3? on your fingers, what do you think the max height is? Okay. I'm seeing a couple 5s and a couple 6s. So I think the 6 might be coming from the fact that you can stack this orange box on here, and then this max height is 4. But you actually can't stack the orange box on this one because 2 is not less than 2. 2 is equal to 2. And remember that the box on top has to be strictly less than. And so the only box that this can stack on top of that makes the highest is the red box. And so the max height here is going to be 5. Okay, now what about at index 4? What, on your fingers, what is the max height? Okay, again, I'm seeing 5s and 6s. So I actually did originally think that this was 5, and then when I was practicing this last night, I actually found out that it is 6, because this box can stack on top of this box, which was wild, and I did not think of that. And so because of that, that makes a height of 6. Okay, now the last one. What is the max height at index 5? Yeah, perfect. I'm seeing a couple 7s. Great work. And so this is using everything that we have sort of come up with and put together. And if you remember all the way at the beginning, the first slide of this problem, the answer was actually 7. So we did it. Great work. And now the next step is writing the pseudocode. And I am not going to go through all of this with you, but this is just putting together all the steps that we sort of answered in the past couple slides. And so I wrote the recurrence up here, and the code is essentially just the exact same thing as the recurrence. So this entire box is just me writing like this for loop and then checking whether these two are greater than the current max height. And then the other sort of things that we answered, like the questions that we answered before, the one about figuring out what order we solve the problems in, that tells us how to write this for loop. And so since we wanted to go from the beginning of the array to the end, we go from 1 to the end of the array. And then also we determined the final answer, and that is just what we return here at the end. So again, the pseudocode is just sort of putting together all of the pieces that we came up with before. Yeah?
A really quick question about the previous slide.
Mm-hmm.
So if, like, let's say the last box had like a dimension of like 100 foot width or something like that, then they can't stack on any of the other boxes. What would the max height be?
It would just be this one, because it's either the max height of this or the max height of this. And so since j is any j in this set, the max of those is 6.
Okay. But in future boxes, will we just skip looking at this one that can't stack on anything?
So if this, so like you're asking if there's boxes after this? Yeah, so I mean, we can always see if there's a box that we can stack on top of this one. But then also the value here, if there is a box that we can stack on top of it, then we would, I'm a little confused. But essentially the value at this index would be 6 if this can't stack on top of anything else. If something else can stack on top of this one, then we have to check the max height of like what that one can stack on top of, sort of. Yeah?
I may have missed this kind of at the start, but are we kind of assuming that we're ordering the boxes in some way coming in? Like if the next box was 10 by 10, it could go at the bottom.
Yeah.
But
So I did sort of just say it like one off, but I have ordered this based on length. And so the length is sort of decreasing, and so that way we know that new boxes cannot be stacked below any boxes before. Yeah. Anything else? Anything about the pseudocode? Okay. Now I'm going to give you guys some time to just sort of look at this and figure out the runtime. I'll give you, actually we only have 20 minutes left. I will go through this quickly and then have you guys answer more questions in the next problem. So this first section here, we're not calling anything, we're not looping through anything, so that's going to be constant. And then we look at this for loop. And so to find the runtime of that one, we actually first need to look at the for loop inside. And this one goes from 0 to I. And since I goes from 1 to n, if this is n, then the inside for loop will run in O of n. And thus the outside for loop, since this one also iterates n different times, is going to run in n squared. And the last return is also going to be just constant time. And so overall, we have an n squared runtime. Any questions? Okay. Now on to the next question. Sorry about random white light. Yeah. Okay, so the knapsack problem is actually a very, very popular dynamic programming problem that you will see very often. It is also very similar but more complicated than the box problem. And so I think it's a nice next step. And so the knapsack problem is we are given a set of objects, so something like this. And each object has a value and a weight. And we also have a knapsack that has some maximum weight, some weight limit. And we want to find out what the maximum value we can have in the knapsack without going over that weight limit. And so again, this is sort of the example input that I have created. And the answer here, so with max weight 3, we can use these two, and so the max value will be 12. So that's what we're sort of searching for. And so again, we are going to identify the cases first, and the base case is going to be the easiest possible problem to solve. And so the easiest problem to solve is going to be the case when there aren't even any objects that we can possibly add to the knapsack. And if there aren't any objects we can add to the knapsack, the max value is going to be 0. Then in the recursive case, there's two situations. So again, imagine that we have this sort of set of objects that we can add to the knapsack. And we know that the max value, using some subset of these items, is like some value, right? So we know the answer to this problem. And we want to add this other item into this set. So if this other item is already over the max weight of the knapsack, then the max value of the knapsack using this set of items plus this new item will just be the same as the max value in these set of items. Does that make sense? Since you're not creating any combinations with this new item. Okay. And then the second case is that this item has a weight lower than the max weight of the knapsack. Thus, we need to combine it with a couple other ones and find out the max weight using this item in the knapsack. And so, in that case, the max value is just going to be whichever is larger between the max value without the new item and the max value with the new item. Any questions so far? Okay. And again, I'm going to write this as a recurrence because it makes the pseudocode part easier. This one is the base case. This is case number 1. And so this, actually, wait. Let me first define these two. So I is going to be the current set of objects that can be put into the knapsack. So I is very similar to I in the last problem, where it's going to be all the set of all objects from 0 to I in the input array. W is then going to be the max weight. And so this one is going to be all weight values from 0 to W. And so when the current item cannot be even put into the knapsack, the value is just going to be the same as the max value without that current item. If it can be put into the knapsack, so case 2, that means that it's going to be the max between this quantity and this quantity. And so this is the quantity without the item, without the current item, and this is the quantity with the current item, because we are using the value of the current item, and we are finding the max value of the weight minus the weight of the current object, since we are putting that into the knapsack, or we are simulating actually putting it into the knapsack. Any questions? Okay. So next step is figuring out the dimensions of the data structure that can store memo. So for this one, we want to look at what all the possible values of I can be and what all the possible values of W can be. So I'll give you guys like a minute to think about this with the people around you. Another hint is make sure they are in terms of the inputs. Okay. I know that wasn't that much time, but still. What do you guys think?
Maybe the length of the input for the height and also the length of the input for the width.
Yeah, so the length of the input is definitely going to be one of them. So this I refers to the set of objects that can be put into the knapsack. And that set of objects, the size of that, is defined by the length of input. However, this one is the weight. And so if we look at the last slide, this includes all weight values from 0 to W. And so this one is going to be dependent on this input of W. The other thing is our base case is when there are no possible items to put into the knapsack. And so we want to account for this empty set case. And so it's actually going to be input.length plus 1. And since we're also dealing with weight equals 0, we want W plus 1. And so the array is going to look something like this, where this is input.length plus 1, and this one, oh Jesus, this is W plus 1. Okay, and now that we know that, the dimensions of memo, where is the final answer going to be stored? Does anyone want to be a brave volunteer and just shout out an idea? What was that? Sorry? 0, 0. So over here. So this one is going to be when max weight equals 0, and there's nothing that we can put into the knapsack. And so if we look back to the original problem, the original problem gave some input of items and some input of max weight. So I don't think that a max weight of 0 with no items that we can put into the knapsack solve that problem. Any other ideas? Okay. Oh, yeah?
Maybe the other corner, like 3, 3.
Yeah, so this one. So this one includes all of the items in input, and it is the actual inputted max weight. And so this one is going to be where the final answer is. And the general indices of that are going to be input.length and W. And now we know that this is where our final answer is. And this is where our base case is. So we know that this is our base case because our base case is when I equals 0. And so that's this entire row. So knowing this, in what order do we want to fill the array in? The other thing you want to think of when solving this, or answering this question, is what indices of memo do we need before computing other indices? So for example, for any I, it looks like whenever it's a recursive case, we always need I minus 1. So do you think we should do level by level, or do you guys think we should do column by column? Okay, raise your hand if you think level by level. Okay, raise your hand if you think column by column. Yeah, so most people did level by level, which is right. So since we always need the previous I value, we want to make sure that this, this entire row is filled out before doing anything in this row. And so now let's try filling in a little bit of this together. Oh, look, I have a little animation. Okay. And so this is our base case, and now we are going to fill in this one. And so this one falls into this case because the weight of item 1 is 1, which is greater than 0. And so we fall into this case. And so the answer is just going to be the value at this index. And so if we go to that index, which is this one right here, that value is 0, so we just copy that over. For the next one, we would do, for this next one, we do a very similar thing, except now we are in this case, since this weight is less than or equal to this weight. And so here, we want to find this value, and we want to find this value, and see which one's greater. So this one we found before is 0, or is this one right here. So that one's 0. And then we know the value of item I is 1, so it's going to be 1 plus the value at this index. So this is going to be, since I is equal to 1, this is going to be 0. And since weight is equal to 1 and the weight of object I is 1, this will be 0. So at 0, 0, we have this. And so this equals 1. And 1 is greater than 0, and so we put 1 here. Does that make sense? Any questions so far? Okay. Similarly, you sort of get 1 for the rest of these. The next one, since the weight is 0, again, this is going to be 0. And then for this one, we look at this second case again. And so the value here, that's going to be 1 because it's this one. We're solving this one right now. And then the value of the current object is 2 plus the weight of this, and so that's going to be 1, and then the current weight is 1 minus 1, which is 0. And so we look at that index, which is this one here, and we put 0 here, which equals 2, and 2 is greater than 1, and so we put 2 here. How are you guys feeling like, about this? Yeah?
I'm just a little confused about the notation. So what does VI mean?
VI is the value of item I. So we are given an I in each of these. All of these are I values. And so VI is just going to be the value of item I. Anything else? Okay, I will give you guys, I'll give you guys like 2-3-ish minutes to fill in the rest of the table on your own. And remember, the actual final answer is 12. And so that should help with at least your last one. So go for it. Okay, so I know that was really fast, but I believe in you guys. So at this index, this point in the array, on your fingers, what do you think the value should be? Okay, I'm getting 2s and 3s. So remember that we can use both item 1 and item 2, and the weight of those two combined is 2, and so this can be 3. And then the next one will just also be 3 because we can't add any other items. What about, actually, this one, since max weight is 0, that's 0. What about this box? What do you guys think on your fingers? Okay, I'm getting 2s mostly, which is right because the max weight is 1. And so the max value for that, even with this one, since this can't be put in there, is just going to be this value here. What about the next box? What do you guys think? Yeah, I'm getting a lot of jazz hands. So this is going to be 10 because this is weight 2, and this max weight is greater than this max weight here. And then the last one, we know that the answer is 12. So I'm going to skip that. But it's basically these two items. Okay. So now, again, the pseudocode is just sort of a direct copy of, and like combination of all the things we came up with before. Base case, recursive case, cases 1 and 2. One thing that's important is the order that we decided to fill out the array, since it was level by level, that helped us find out that the W for loop goes inside the I for loop, because we wanted everything in the row of some index of I to be filled before moving on to another row. And then for the runtime, that's pretty straightforward too. This for loop runs in O of W. The inner for loop runs also in O of W, and so the outer one is going to be n times W. So overall, we have an n times W runtime. And I just wanted to show how impressive this actually is, because if you did a recursive version where all of these were actually function calls, then those would loop on their own too. And so you would get this sort of tree structure that would cause it to be in O of 2 to the n. And so that runtime compared to NW is so much worse. Any questions actually so far, last minute? Actually, we're like a minute over. So yeah. But these are some more examples. Thank you so much for coming to lecture today. Good luck on the final. Oh yeah. I will be there as well. Thank you.